Hi and welcome to Unit 1, Topic 1, Video 7. And in this video we're going to be continuing with permutations and looking at a really common context of permutations with like objects. So let's say like objects. In a previous video we talked about a couple of examples where the objects were distinctly different, like people going to a cricket match. In this video we're going to talk about what if the objects are like, so if you interchange them it actually won't make any difference to the final result. So let's have a look at example 3. How many ways can a 7-letter word be made from the letters in the word? History was our previous example, but this time we're going to say balloon. So balloon is interesting because unlike history, which has 7 distinct letters, balloon has 2 pairs, 2 L's and 2 O's. What if the word was actually balloon? So let's go through and have a look at our calculation in this case. So, how many ways are there of making a 7-letter word from the word history? Well, that's 7P7. So 7, and we choose 7. And the same goes for balloon. So the answer here is 7P7. But the problem we've got is if you have L1 and L2, and then we have L2 and L1, well, that's the same word. So for example, a mix-up would be B, L1, O, O, L2, NA. Would be the same as when we get this word, B, L2, O, O, L1, NA. And to throw further complication in, we've obviously got O1 and O2 as well. But what we need to recognise here is a pretty simple case where we just have 2 pairs. So L1 and L2 can be swapped to give L2, L1. We can just reverse the order to get the same result. But we can only reverse that order once. So that means basically we've double counted everything. So we just need to get 7P7 and divide by 2. And of course, this is for the L's. What about the O's? Well, to sort that situation out, we'll just have to divide by 2 again, and that will determine our final result with the O's included as well. So technically, this will be 7P7 over 2 factorial, and that will be equal to, in our calculators, 1260. So this is by considering that the 2 L's are the same, therefore we've double counted, and we have 1260 ways of coming up with a new word, which is 4 times smaller than the 5040, which would just be 7P7, if, for example, is the word history. So then we've got the, what about a 4-letter word with the word balloon? So this is a bit more problematic. And it does take a bit of work, and just for your benefit, I'm going to run through it now. We don't have a lot more to work through, so I'm going to run through this one now and show you how we can deal with a question like this. But to be honest, it's unlikely to come up with an exam because it's a bit tricky. So we've got this. We've got B, A, N. They're our good, nice letters. And then we've got L1 and L2, but they're not distinctly different. And we've got O1 and O2. So because we're talking about a 4-letter word, we're dealing with this. Now if there's 2 O's in there, well then we've double counted because you could flip those O's and you get the same word. But we don't know if there's 2 O's in there. We don't know if there's 1 O in there. We don't actually know if there's no O's in there. That's our problem. So we're going to deal with cases. Case 1, we'll start at the high end. Case 1 is that the word contains the letters O, O, L, L. So how many ways are there of doing that? Now, if the word contains exactly those letters, then there's 4 ways of sorting out the 4 letters O, O, L, L. We have to divide by 2 factorial, because we've double counted the reversed L's and the reversed O's. So 4P4 divided by 2 factorial is 6. And I'll highlight that. That's our first one. And then we're going to have a look at case 2. And in case 2, what if there was 1 O but 2 L's? So we've got O, L, L, and then 1 other letter. So in this case, we've got a few things to consider. There is one way of choosing the first O, times by 1 way of choosing the L, because we're given that, times by 1 way of choosing the L, keep on writing L, times by 3 ways of choosing that last letter, B, A, or N. And that gives us 3. But of course, it's a bit more complicated than that because we could organise that in 4p4 ways, and we could swap the L's, and we could still swap the O's. So we've got an O in and an O out. So we've got to do a divided by 2 factorial twice, and this gives us, I'll keep on going wide, this also gives us, well no, not quite, it gives us 18. So we get 18 there because it's 3 times bigger than our previous answer, and I'll highlight that. And of course, this case 2 is incorporated in the same as case 3. And case 3 is L, O, O something. And so that's also 18. So we're getting that. And then we have case 4. Case 4 is where we consider the situation where we have one of each. So we have an O, and we have an L, and then we have a blank and a blank. Same logic, 1 times 3 ways of choosing the first blank, times 2 ways of choosing the second, times 4p4 ways of organising once they're all chosen, and then divided by 2 because the O and the L could be swapped in and out for each other. And so this calculation gives us 36. These numbers are pretty small, which we can expect. But we've got to keep on going because there's other options, such as case 5, which is O blank blank blank. So there's one O and then no L's. So there's one way of choosing the O, times by 3, times 2, times 1, times 4p4, and then this time it's just divided by 2. Because previously we divided by 2 factorial twice, but because the L's aren't included, we don't care which order they're in and which one was selected. So we divide by 2 once, which gives us 72. So we're building up slightly. We have a case 6, which is L, and then nothing, nothing, nothing. And in this case, we've got one way of choosing the L, 3 times 2 times 1 times 4p4. I didn't even need to write this down because it's exactly the same, and that's 72 as well. That's the same as case 5. And then we've got a case 7 and 8. So case 7 is where we have a double O and no L. And so this is 1 times 3 times 2 times 4p4 again. And then this time again divided by 2 because the O's could be ordered in 2 different ways. And so it's exactly the same as above again, which gives us another 72. And case 8 is the same again, but with the L's. And so that gives us a 72 as well. So I'll highlight those two. And I'm running out of space a little bit. We'll add a bit of space. We need to consider this one more thing. So we've got all O's and L's, 2 L's and 1 O, 2 O's and 1 L. One of each, just an O, just an L, or double and double. And the only thing that we're missing is case 9, which is no L's and no O's, which means we get to choose 1, 2, 3, but then we're out of letters. So there has to be at least 1 O or 1 L to make this work. So therefore we've got 0 there, and now we just need to simply add up. So 72 plus 72 plus 72 plus 36 plus 18 plus 18 plus 6 is a total of 366. So there you got that example 3 carried on a little bit too much and probably beyond the scope of what you need to do, but it's really good to play with these questions and get an idea of using the case-by-case situation. Okay, so now let's have a look at example 5. So this will be our last example and then we'll finish the video. Firstly, how many ways can 7 red books and 4 blue books be lined up? So in this case we've got 11 objects and they're 2 distinct colours, but the assumption we have to make here is that the 7 red books are distinctly the same, and if you swap them it won't make a difference to the order, and the 4 blue books are the same as well. And so therefore we'll get this. There are 11p11 ways of choosing the complete order, and 11p11 is equal to 11 factorial. But we are also dealing with the fact that there are 7 red books and there are 4 blue books, and so we have to consider double ups. And in this case the double ups go a little bit deeper than we're used to, because it's not just 2 factorial anymore. The 7 red books could be interchanged 7 factorial ways. So we have 7 factorial, 4 factorial as divisors. which means that we have equals 11 factorial over 7 factorial 4 factorial. And that's our new fractional situation. We can simplify this. You could put that straight in your calculator, but just in case this comes up as, let's say, a tech-free question, well, this works out to be 11 times 10 times 9 times 8 times 7 factorial over 7 factorial times 4 factorial. Of course, 7 factorial cancels out. The 4 factorial can be written as 4 times 3 times 2 times 1. 4 times 2 is 8, so that can cancel out. 3 and the 9 can cancel out to leave 3. 11 times 10 is 110 times 3 is 330. So you can see you can do that one without a calculator. But there are 330 ways of lining up 7 red books and 4 blue books where the red and blue books are distinctly the same. And then final question, how many ways can the letters in the word Mississippi be arranged? So Mississippi has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters. And so the number of ways is 11 factorial, 11p11, divided by all the double ups factorial. So there are 4 S's, there are 4 I's, and there are 2 P's. And so we end up with 11 factorial over 4 factorial, 4 factorial, 2 factorial, which is going to be something a little bit larger. And we could simplify this, but I'm just going to put it straight into my calculator. And that comes out as 34,650. So keep in mind that you will only have to deal with non-calculator and tech-free questions and tech-free exam papers, but you can also deal with, which one should I practice with by considering 11 factorial is a really large number. And the only way to make that manageable is if it's divided by something reasonably large factorial. The 7 factorial up here did enough. The 4 factorials don't really do enough here, and the little number remained large. So it's not really worth dealing with by hand in this case. So there we have it. That's the end of permutations. There are lots and lots of different styles and types of questions. It's definitely worth playing around with your textbook and other resources you have and making sure you ask your teacher questions.